All right. Hey, folks, we're going to go ahead and get started. So by way of introduction, my name's Jason. I'm with the Google product management team focusing on AI infrastructure. And today we're going to be talking with some panelists across a variety of industries. And we're going to get into some deep dive topics around how they're using AI infrastructure with Google and solving some interesting challenges. So just to kind of set the stage a little bit, I'm just going to go through a couple slides to explain a little bit about this main technology that's going to kind of ground a lot of the different use cases you'll hear about today. So it's what we call the Google Cloud G4. This is based on the NVIDIA RTX Pro 6000. It's what we call the universal GPU. This is something that sort of sits in the middle. It's not really at the high end for massive, training of, classic models, model foundation builders, but it's also not at the very low end. It kind of sits in the middle, and it's really good at a lot of different things. It can do, small model inference, small model training. It's really good for graphics use cases, things like Omniverse, digital twins, simulation, things like that. We've done some unique things to this, and just want you guys to understand what that is if we end up kind of talking a little bit about some of these terms. So one of the things is we've built this peer-to-peer technology as we've deployed these at Google. And what that means is you can get some significant performance benefits than just any other RTX Pro that you might find anywhere else. So we've built this unique switching technology that allows this to sort of communicate almost in an NVLink type manner. So NVIDIA has these NVLink switches that really help offload GPU to GPU communication. And you get those in the higher end GPUs, the GB200s, GB300s, things like that. The RTX Pro doesn't come with that, right? And so they can be a little bit slower to talk to each other for like all collectives, that types of communication, GPU to GPU. So we built this peer-to-peer design to actually offload that in a unique way. And you just get that out of the box. It's real simple to use from a G4 out of Google Cloud. And what that looks like is significant performance boost from a throughput perspective. So this is just showing, a open source Llama model and comparing if you just had a regular RTX Pro compared to the peer-to-peer turned on. And so the more you start to scale these, the more you get some significant performance advantages. Same thing with reducing latency, right? So significant latency reduction in terms of how this benefits. The other thing you'll hear us talk a little bit about is cost considerations and cost advantages. And so actually, literally today, the fractional G4s are generally available. And so up until today, you could get 1, 2, 4, or 8 GPU systems. But now you can actually get out of the box through Google Cloud VMs that are an eighth, a quarter, or a half of a GPU. And we're going to talk a little bit about what the advantages are there from a price performance perspective. So with that, I'm going to go ahead and invite our panelists on stage. So Perry, Sony, Shane, please come and join us. And so we're going to have them each introduce themselves, a little bit about what they do and what their organizations do. So Perry's going to go first. Perry's with WPP. They're doing some really interesting things with robotics. Sony is with General Motors, doing some really interesting things with autonomous vehicles. And Shane is with Schrodinger, doing some very interesting things in the life sciences space. So Perry, go ahead, introduce yourself, a little bit about WPP and what you do there.
Yep, my name is Perry Nightingale. I've been head of creative AI at WPP for 5 years, and I used to have to spend the first year explaining to people what that was, but I don't need to do that anymore. And WPP is one of the largest marketing services organizations in the world. So about 100,000 people. Anywhere you can buy shampoo in the world, there's probably a WPP agency, so that's everywhere. And my role is to look at generative AI and physical AI in production.
Great.
Hi, I'm Sony Mohapatra, director of the AI ML infrastructure team within GM. My team owns orchestration, compute, and inference platform, essentially helping GM build AV for personal cars. And across evaluation, training, validation, and large-scale simulation. The mission of my org is very focused. That is to build the next generation AV infrastructure to accelerate the iteration speed for AV development workflows within GM.
Okay.
Hi, I'm Shane Brauner. I'm the CIO of Schrödinger. We're a digital chemistry company. So we do everything designing molecules for discovery of new drugs as well as material science. So we've been in this space for over 35 years, and it's really exciting to see how the power of computation as well as the advancements in science are really starting to change the game here.
Great, awesome. So got a pretty diverse mix here, so it's going to get some really good perspectives. I think we'll start the conversation around simulation, and we'll start with Sony. From a General Motors perspective, building autonomous vehicles, it's really a massive simulation challenge. Be curious to hear your thoughts around how you guys are approaching that, how the G4 helps.
Yeah. So yes, absolutely. It is a massive simulation challenge, but G4 has changed the way we scale our simulations. Just from the throughput standpoint, when we did a controlled apples-to-apples comparison with G4s and a quad L4s, we saw significant improvements, a 20% reduction in total runtime, and then it went on to a 38% when we ran production level workloads. It reduced a 38% reduction in compute time, and this means that we could essentially be able to validate more scenarios, and that was of the order of 40%. This is significant looking back. And then as we moved on, we saw other performance metrics, such as the CPU-driven phases improved by 50%, the GPU-driven phases by 20%, and this combination was very useful for simulation because that increased the run rate for simulation by 20%. And all of these nuances just added to the way we were running regressions, the way we were finding issues early on in the cycle. Also with the GPUs, the G4s, they use hardware efficiently, so very good bin packing, great GPU utilization, much smaller GPU idle pockets, and that way we didn't have to wait too long just wasting our GPUs and spending money on that. So overall, I mean, what we saw is, I don't know what you guys did, but from L4 to G4s, it was great, and the metrics that you showed, I can watch for it and validate that.
That's awesome. That's great. We love hearing it in practice. So if we continue the simulation theme, Shane, you guys have an interesting problem space. I mean, take us through a little bit about just the sheer scale of how you think about what you're tackling and what simulation means at Schrödinger.
Sure. So the drug discovery landscape is vast, and this is where a lot of kind of AI-only approaches tend to struggle. There are more drug-like molecules possible than there are stars visible in the night sky. It's something like 10 to the 60th power, right? It's just this massive, massive space. And every time you have a protein that you're trying to find that sweet spot to either activate it or deactivate that protein's function, that's a different problem set than you would have from another protein. And so it's really, really difficult, if not impossible, to assemble a training set to cover the entire drug-like molecule landscape. So one of our approaches is to take our physics-based approach and use that to generate data that is then used to form a training set that we can use to prosecute and run inference on a larger set. So we'll typically start with a virtual library of molecules, say 8-10 billion molecules that we'll use, cherry pick a handful of those, run some more expensive, computationally expensive physics-based calculations to generate synthetic data that we then use as a training set to score the other 8 to 9 billion compounds in that library set. Then we'll repeat that as further refining as we go, down to a smaller set of molecules that we'll use to really start the interesting iterative process of designing a molecule that meets all of the different optimization parameters that we really want to get out of a good drug. It's soluble, it binds to the protein in a way you want, it doesn't bind for too long. All of those different parameters is the next step in the drug discovery process.
Yeah, very cool, very interesting. Perry, I mean, over to you from a simulation perspective. I mean, you guys are using all kinds of different robotics. I think some of it's experimental, some of it is being used in practice. How do you guys think about simulation in terms of how you're deploying, these systems, I guess through the use of media?
Yeah, I mean, advertising is one of the most high-tech businesses in the world. It's your business. and Meta's business, and obviously have huge AI divisions, right? So there's an enormous amount of compute that goes into that generally. We're massive, one of the world's largest BigQuery users, WPP. But my role is actually in the content creation side. And we do a lot of 3D rendering because generative AI still struggles to get products the right size and logos correct, and so I work very hard on solving those problems. But as long as people are watching stuff on bigger screens, they need decent content. So we still shoot traditionally quite a lot, and the last couple of years has seen a lot of advances in robotics in that space. So we simulate humanoid robotics for camera work, quadruped robots for camera work. So on the AI infrastructure stand in the expo, you can see our robot dog with the camera that we've worked on with Sony, and those are all simulated in Isaac Lab. And I have the honor of testing these machines for you, and therefore for NVIDIA as well. So we were one of the first people to run a complex multi-GPU simulation in Isaac Lab, and it didn't even report properly for multi-GPU when we did those testing. So P2P is a really powerful tool for doing massive simulations of robots in Isaac Lab. We went from 12 hours to something like 30 minutes. And I don't know if anyone's done reinforcement learning in robotics in the room, but you have to make a tiny change. She might go, I'm going to increase the surface friction of the robot's foot, right, to try and, to sort of teach it something. Having to wait 12 hours to see the effect of that one little change, is just, it breaks the whole thing. So to put that down to 30 minutes is an absolute game changer for the work we do.
Yeah, it's been a lot of great proof points in terms of, like Perry was saying, how some of these technologies have really rapidly reduced the time it takes to do things. So speaking of, reducing time and the impact of that, Shane, maybe explain to folks a little bit about predictive toxicology, what that means to society, what that means to, what you guys are doing, and how all of this is helping, accelerate.
Sure. So toxicology, so drugs, especially potential drugs, can have toxic side effects. That means they're typically going to be attaching to a protein or a molecule in your body you don't want it to. It's going to have some unwanted effect. One of these is called a hERG receptor. That governs how your heart beats. And so if you have something that binds to the hERG receptor, it's going to block the potassium flow, and you're going to have a heart attack. So we really want to make sure our potential drugs are not going to bind to that hERG receptor. There's a whole host of other different kinds of, we call them off targets in your body that you want to make sure that you're not going to bind to. So the way that's typically assessed is you'll create in the lab your molecule, and then send that off and run a series of tests, physical tests with that. It takes about a month to do. And that's after you have your molecule synthesized, which could take weeks to months to do that. So our approach with predictive toxicology is rather than wait, and that's potentially a couple of years down the line when you're actually synthesizing things after you've been after you started your program, is to move that, we're shifting that left in the whole drug discovery process. And so by doing this virtually, so instead of actually having to synthesize the compound, you're able to do it in silico in the computer system, and we'll run a series of digital assays and do these simulations and seeing, are we going to hit hERG? Are we going to have a problem processing kinase or other types of things in your body? And we'll be able to learn that in minutes. Similar to what Perry was talking about, this being able to shift that time frame from weeks to months to hours is a really phenomenal difference for a program. And that can mean real money. It also can change the way that you're thinking about the problem space that you're in. Rather than it being a really restricted type of thing that you're going to engage in, that level of testing, by shifting it earlier in the process, by making it faster and cheaper, you're able to do more of it. And you're able to look at things you might not have otherwise looked at. And that type of opening the potential area of the things you're going to be exploring and looking at, that can be a game changer, because you might be looking at something you otherwise would not have looked at.
Yeah, that speed is a commercial advantage. And especially with robotics moving from academia, who have all the time in the world. Like, I work with Oxford Uni, they've been around 1,000 years, and you do a project with them, and it's like 3 years or something till they get it out. Whereas, if you're in a robotics startup and go out on the expo floor, there's a ton of them, and you wanna compete with other startups, compute is one of the areas, right? You can go out, you can get investment, and you can spend it on compute, and you can do the same project in a tenth of the time, and that's the shift. And you saw that 5 or 6 years ago in AI, where people went from having 1080s and these sorts of GPUs, which they probably loved gaming on at the weekend, in their little sort of uni labs. When suddenly people were selling AI services to people as startups, that's when the cloud consumption kind of rocketed. And you're seeing the same thing in robotics, I think, now.
Yeah, I think that's, pretty strong theme at the show so far. A lot of what you probably all heard yesterday is just that, right? The relationship between, the amount of compute, the power of compute, and how fast things are moving from a competitive advantage perspective.
But compute not only for robotics, but now with agentic, there's compute needs there as well. And overall, compute is the most important thing right now, I guess.
Yeah. It's we're going to jump to a quick relationship between compute and tokens, and what all that means in the agentic world. So, in terms of compute and scale, Sony, so you guys are dealing with a massive amount of sensor data. How do you guys think about the relationship with some of this new compute as it relates to that and inference, and how you're managing all that from the sheer scale of GM from an autonomous vehicle perspective?
Yeah, so the G4 inference throughput has allowed us to move more sensor frames per second. And with that, we've got like 8x increased RPS, and we have 8x faster runtime, 4x faster time to result. And this is not only because of the GeForce, but also the architecture we chose, right? So we selected an architecture where we are not streaming data anymore. We are preloading them. And also the analysis and download phases have reduced in time. So idling is no longer a problem. GPUs are not waiting for I/O and pre- and post-processing steps anymore. Also, inference has become very important in the current state of the world. Earlier, the models that were coming out was not so much in line with autonomous driving as such. Now, more and more models are able to cater to our autonomous driving models as well, and experimenting and getting those inference into our pipeline is so important. We currently have our P90s with an 80% GPU utilization, and our P50s at 50% GPU utilization. So we have more coverage without really extending the build validation time. And this means faster iteration. We are able to get regressions faster, and we are able to iterate a lot more over different kinds of models out there. We have built our stack internally because our scale is so high and our requirements are so different that with that stack, the combination of this compute just works beautifully.
That's great. Maybe let's shift a little bit to like, adoption of this technology and how we think about the cost sensitivities and the availability of these scarce resources. So we mentioned earlier, right, that today we're making generally available these virtual GPUs. Shane, I'll maybe go to you first. How do you think at Schrödinger in terms of price performance as you start to tackle some of these challenges and balancing what's available? What does the advent of these fractional GPUs mean to you, and how you think about price performance at Schrödinger?
Sure. So price performance has been my North Star forever. We've been building GPU clusters using GPUs since about 2012 with our stack, and we scale really well horizontally. So that means that it's not just about the speed of a particular GPU. It's about how many GPUs we can bring to bear on a problem. And so that means the cost per GPU is really important to us. And so being able to right size that GPU for the problem that we're trying to tackle is really important, because it's really easy to start to pay for memory and bandwidth and other things that you don't necessarily need for this problem set. So this is why the G4s, and especially the fractional G4s, are really important for us, because not every problem is a really big, large memory problem or big compute problem. And so being able to size down and say, you know what, we can get by with less than 24 gigs of memory for this problem set, and utilize them in that way can really help us cost optimize, so we're not paying for things we don't need.
Nice. Yeah. I mean, that's one of the things you'll hear a lot from us is our approach from an AI hypercomputer perspective overall is just that, right? Is we're trying to constantly figure out how to provide the broadest set of capabilities to our customers so that people have the flexibility to, deploy what they need based on their workload, based on, the size and scale that they need. It's not always a one-size-fits-all, right? I mean, Perry, I think you have a unique perspective on this as well in terms of how these different costs play out. And
yeah, I mean, I got the creative AI role sort of 5 or 6 years ago. Did a bunch of early experiments, saw that these things were going to be challenging to scale back then. This is before ChatGPT, to be honest. And so we pulled back a little bit, actually. And the Mandalorian documentary had just come out, and my boss was like, I'm really interested in 3D and deconstructing adverts. The way films are being made is changing. Let's change the way adverts are made. And that actually led me to Omniverse and the NVIDIA team behind that. And we were one of the first people to look at that, right? It was Foster's and us and Volvo and a couple of others. So we started working heavily there, got on a few sort of big NVIDIA keynotes. And NVIDIA really has 2 jet engines. One of it is data center, and the other is simulation. And data center sort of really 3 or 4 years ago massively overwhelmed the other side of those things, right? So I carried on in simulation, but obviously data center and agentic sort of took off. But to run those Omniverse renders at scale for our clients, there was nothing in the cloud. There were no RTX 8000s in the cloud. There was the L40s eventually came, but there was no high VRAM cards in the cloud for rendering because there's massive power consumption, and the demand wasn't there. It was basically just me, to be honest, I think, at that point. And so I had, at one point, 29 A6000s in my house. I mean, it was the noise of that, and it was heating the house, basically.
And the power bill.
Yeah, the power, my electricity bill, my nearly getting divorced because of my electricity bill. And, I had my daughter, she's 3 now, Willow, and she actually used to sleep when she was just born. She used to sleep next to the render farm because it was like this warm noise continuously. Right. Yeah. And Jensen actually sent her a baby grow to say thank you for all the work we were doing. I wish he'd sent shares, to be honest, but he sent like a little message saying congratulations on Willow, right? So that was we were at the center of that work. Yeah. And to see cards like this in the cloud is actually a major inflection point, because at one point, I'm going to sort of share this with the room at a public, they nearly gave up on Omniverse. Data center was so huge, and the demand for Omniverse was so small, that they were sort of thinking, do we really want to keep pushing this? And then a year ago, suddenly they realized this is where robots will live and learn. And now, the way they've architected their GPUs, they have a brilliant card to play in the physical AI future. So, I think it says a lot about a company like that they keep going, even though they're not totally sure where it will end up. And I really have seen that with Omniverse. And now, you can get 8, RTX 6000s, and you don't need to blow up your garage like I nearly did a couple of times. Right. You can do it in the cloud, and you can do it in any market in an instant, and you can scale it up and down. That's the difference.
But as doing a lot of research and stuff, I think from a cost perspective, it's not like you have the budget of these big enterprises necessarily, right? So I think the fractional stuff provides all kinds of flexibility for you there, doesn't it?
Yeah, 100%.
Yeah. So Sony, I think it'd be interesting for folks to understand, you guys were using some of the previous generation versions of these things in the cloud from Google Cloud. Take us a little bit through the journey of the decision making, the trial and error. You didn't just jump into these new things just because they're the latest. What went into the decision making? Yeah. What was your process? And then once you decided to go about this, how did you kind of adopt these things in your organization?
So it is a very data-driven process, for sure. We were using L4s, and when we took a look at GeForce, it was a leapfrog. It wasn't just a switch of GPUs, because there were dependencies such as CUDA versions and machine images, and all of that. And we had to work through each of those in order to make this transition. And this transition was really important because the performance was a consistent story. When we ran it in a controlled environment versus when we ran it with our production-like workloads, the performance remained consistent in the increase. And GeForce had a very compelling case for us in terms of the increased throughput, the overall performance cost reduction. And really, nobody talks about cost in terms of developer cost as well, right? We talk about dollar costs, yes, and we try to map it with our older systems, and we do all of that in the budget. But the fact that this also brought down developer cost in terms of reducing the time to result, for example, and increasing iteration speed, I think all of that adds up to this decision of moving to the latest chipset. And we're not going to stop at GeForce. We're going to constantly keep looking at what is the next generation chipsets that you have in order to unlock all of these metrics, not just one particular aspect, as some might be very focused on, say, dollars or performance. Because there's always a tug of war between money and efficiency. You can throw a lot of money and get the best efficiency and be fast, but that's not always the right direction. So this was a good balance of yes, we could save our dollars as well as be fast, reducing the developer cost as well. So all of this led to getting to the G4 transition. We worked early on with GCP, partnered with them, and identified the issues much ahead of the time, and then did a ramp up of the G4s. We also saw that there were no firefights along the way because we started early. So I think that is the advice I would give anybody who wants to move to a new chipset, is just get early on. I think you guys are great partners with supporting. So it just worked out with minimal issues there.
Yeah, good. I mean, and so there's definitely something to be said for adopting the latest hardware, and of course, some of the innovations that we put in there, and to your point, the close partnership and how seriously we take it to make sure it works well for our customers. But there's also, I mean, we take very seriously the whole stack, and the co-engineering, co-design work that we do internally on making sure things like GKE or storage services or the networking services work really well together with these things. So it's not just the hardware per se, right? It's not like you can go get the same experience by deploying the new, latest chipset in your own data center. Anything you might want to add about just how your team thought about these other services from GCP that you guys use as well?
Yeah, so I like the fact that we have established a very good expectation and process for like incidents, say for example, providing support during these incidences. That's primary, because if there is a SEV-ban, then there's going to be a lot of developer velocity reduction. People are wasting time waiting on the hardware to come up and things like that. Apart from the support aspect, I've seen very close collaboration from engineering teams, and I think that's changed the way we think, because sometimes we don't know the detailed, underlying nuances of certain chipsets, and just learning this from the horse's mouth, I think kind of helps us build systems which can scale, be more reliable, and be able to continue with the same speed. I think that's been really good with Google. I haven't seen so much from other vendors where engineering teams are so closely collaborated, but you guys did a great job, and we've had multiple work streams looking into certain problem spaces, for example, which we may not be looking in immediately to adopt, but along the way we want to adopt it. And all of this information flows in a very seamless way. I don't have to wait on a roadmap. We have like a very good cadence, and I think that really helped the team move forward and much faster.
Very good, cool. So we've talked about simulation. We've talked about kind of price performance, inference, scaling, those sorts of things. I'd like to touch a little bit on some of the newer projects. So let's talk a bit about Gen AI. So Shane, I know you guys are dabbling in some interesting things here. Some of it is about expanding and scaling the use of some of these complex tools, whether it's to, increase the productivity of experts, or whether it's to democratize the availability of some of these tools to a broader user base. Maybe even want to touch a little bit on just, bias in science. Take us a little bit about how you guys think about that, what kind of Gen AI things you guys are building or dabbling in.
Sure. So designing these molecules is something people have a lot of opinions about. And as we work with companies, one of the things that we tend to have a good conversation around is what molecule will we actually synthesize yet? What does a good molecule really look like here? And with a lot of these experts in chemistry, you have a lot of expert opinions. And one of the things with our platform that we're doing is being able to bring a lot of data to this problem. So we have an approach around de novo design. So how do you iterate through and design a molecule and iterate through potential aspects of that molecule? How would you change it to be more effective? And we have ways to do that generatively. And that can result in some non-traditional models or molecules that, when somebody looks at it, they would say, I never would have made that. I never would have suggested that. But it looks interesting, and it's scoring well in all of our digital assays, so let's give it a chance. So those types of things, everybody has a bias. If you're human, you have a bias, right? And so being able to bring data, and not just data, but like data grounded in physics and that physics-based truth, that can really be a game changer. Now, when you start to talk about democratizing the access to our software, that's a big thing we're looking at, and I'm excited about this future. So right now, currently running our software is a pretty complicated thing. We have a whole education team there to help people understand and learn how to use our software. It's a very expert system. And so we're working with an agentic approach to have an agent who understands how to run our software as an expert, that's grounded in those basic and advanced concepts of chemistry and drug design, and as well as our software. And so being able to set up a calculation, to run the calculation, to interpret the results when it comes back, and then set up another calculation to run following that, to basically prosecute a whole program. That's one of our goals. It's a really interesting concept, because it then frees up the human to, instead of working with the different flags and settings and how do I structure this input, just take a step back and look at the broader program and think about, hey, how are we approaching this? Is this the right approach? Is this the right way to go? It's a real game changer. I know our teams internally have been blown away by what we're seeing so far.
Yeah, it's exciting. It's interesting. Hearing a lot about agentic this week, and it's always refreshing to hear about how this stuff is playing out for real, where there's real world stakes at play here. Perry, thoughts on the Gen AI stuff on your side? And I think maybe you can touch a bit on the human element. I know you have some very specific views on that.
Yeah. I mean, Gen AI, this is an amazing time to be a creative person. It's a little bit harder time to be a creative company. When your business is selling creative content, we're the largest production business in the world as well. It's really challenging. And, it sort of, I've spent a lot of time lecturing and doing work around computational creativity, which is, like AI to come up with new products. And, Move 37 is a famous example of like a creative move, right, in the game of Go. And funnily enough, like I've used this example in the last sort of few weeks. Willow she's 3 now, about this big. And I had a bag of jelly beans the other day, and I said to her, what color jelly beans do you want, Willow? And she said, 6. And that actually stays with us our whole lives, that illogical answer, right? And so when you say to someone, what do you want to watch tonight on TV? They're like, good-looking people and dragons. And there's no way to actually encode that, right? Because it's actually closer to Shane's world. It'd be really interesting to do like a little bit of a collaboration around, that, because it's intrinsically biological, our response to stuff like that. And we're a long way from recreating those things in our physical LLMs, right? And AI today is metal and sand. That's like, it's in the end, that's all it is. Mm-hmm. And, I think in the creative world, where you've got to come up with an idea that's going to stick in someone's mind and is going to make them choose one almost, very similar thing to another, like water, for example, like that is, we're a long way from machines that can do that. Right. But obviously, you can create a film now in an hour. So we have to adapt to that world and find that balance. And we do that, actually, by investing in talent, largely. Yeah.
Yeah, so I think we're kind of going to start to wrap up here. We've just got a few minutes left. I'll just ask each of you to just give us, maybe a minute or so view on where you see the future going next 12, 18 months in each of your areas. And then we've got a little treat. If we have a minute left at the end, we'll show a neat video of what WPP is up to, and Perry can kind of take us through it. But Sony, what do you see coming in the future?
Yeah. So looking into 12 to 18 months, I think the biggest challenge is for us to scale AV development to support GM's eyes-off capability. And this means that we have to raise the bar for infrastructure, because we will be processing large data sets. We are talking about validating scenarios over a broader spectrum, and training maybe complex models at that point of time. So infrastructure needs to be able to scale quickly to be supporting GM's goal. And I think that is the question. Can infrastructure scale that fast, given that we have tremendous amount of growth in terms of complex models and data and all of it, and be able to provide the eyes-off autonomy that GM is looking towards? GM has announced eyes-off release to be in the Escalade IQ in 2028. And that puts a lot of pressure on infrastructure, compute, orchestration, and simulation scale as well. That's where I would say Google and NVIDIA come into picture. Google's roadmap with respect to GPU evolution, next generation architecture, helping us through GPU utilizations and getting rid of I/O bottlenecks. All of this directly impacts the validation we need for eyes-off systems. And similarly, NVIDIA has their trajectory across GPUs and simulation pipelines, which help us to be able to scale simulation, validation, without really increasing the overall time. And together, I think we can move to, from the systems that we are at today to a truly eyes-off, capability, and with an infrastructure which enables faster iteration reliably, most importantly, and be able to scale at the pace at which we're going. Having driverless cars on the road is one thing. Having your own car where you can just switch off, read something, and be able to drive, I think that's where we all want to go. And as soon as we can get there, that's what's going to get us far, all of these little things along the way. The journey is what matters.
Yeah, I'm both excited and afraid for what this future looks like.
Absolutely.
But it's interesting for sure. My gosh, and it's right around the corner. Shane, just some quick closing thoughts for you. What's kind of the 12 to 18 month window look like in your world?
Yeah, 12 to 18 months. That's both near term and also, a lot of things can happen in the next 18 months. I've been in high performance computing for over 25 years and at Schrodinger for more than 17. And I think one of the directional things that was true when I started and is still true is we're limited by really two things at Schrodinger. It's our ability to understand the problem, what's going on scientifically, and translate that into code, and then be able to take that code and actually compute it and calculate it and get an answer out in a reasonable amount of time. And that's directed by how fast are the computer systems. And so both of those trajectories are just going in one direction, right? We're not forgetting science. And we are, the power of computers is growing exponentially. And so that means the problems that we can tackle, the fidelity by which we can calculate the solutions are getting better and better and better. We're able to do a lot more, and we're able to do it faster as well. And so that's really exciting. There's nobody here in this room, I'm going to go on a limb and say this, whose life has not been affected by some form of disease, right? And our mission is to tackle that, to help improve that, to help change this industry and speed it up of how we are finding cures and treatments for disease. So that's what gets me going every day. And so I'm really excited about being able to accelerate that and help it go faster.
Yeah, I'm excited about that too. I mean, I don't know if any of you had a chance to catch Jeff Dean and Amin's talk yesterday, but there was an awful lot of societal impact motivating them, and people in their shoes who really have a pretty good view of the next 5-10 years. I think we're going to see some of these things actually come true. It's really exciting time. So with just kind of the end, Perry, why don't you take us home and kind of walk us through this montage that you guys have from WPP.
This was for Mark's AI infrastructure yesterday. It's quite humble hearing you know, we're going to self-driving vehicles and saving the world's health, but this is great advertising. So this was made for International Women's Day. We don't show clients ads that have been made with AI for obvious reasons, but this is us opening the curtain a little bit on our own creative process. Everything you saw just then was generative AI, but this is the robotics work we've done over the last 5 years. So we started scanning with Spot, and that led to this amazing project with Boston Dynamics, filming with Atlas. So this is a 15-kilo camera. You know, our human camera operators can't hold these for more than a few minutes. So amazing that you're seeing robots starting to come into these types of environments, right? But this is, you know, a lot of 3D rendering. So, you know, obviously to get the products accurate, we use a lot of Omniverse, and we combine that with these. You know, it's hard to imagine those aren't real, those animals. But I really wanted to end on, it's amazing talent that assembles this, right? Like there was 5 or 6 brilliant female artists who worked on that piece of work. And there's a narrative at the moment that, you know, that you shouldn't hire young people, or that, you know, that AI is really damaging the prospects of young people. And we do need to do a lot of thinking around that. But the money we've spent on junior talent has been the best investment we've made in the R&D budget in the last few years.
Love it.
Yeah.
Well, with that, these are some other sessions that you might be interested in that sort of dovetail off some of the things we've been talking about. But I very much want to thank my panelists here, Shane, Sony, Perry. Thank you very much for a great conversation. Thanks, everybody. That's our session.
Thank you.